Thanks everybody for joining. Today we're going to have a talk by Corentin Talik. He's visiting us from Saclay, where he's finishing up his PhD with Jan Olivier. Camille and myself met Corentin at ICML this year, where he gave a great talk, and some of that he's going to touch on today, and also some of his past work published at iClear, I believe. So, hand over to Corentin.
Thanks a lot. So I'm Corentin, and today I'm going to be talking about invariance to time discretization in the context of machine learning, with specific applications to RL and to RNN training. So first off, just a tiny bit about me. So I'm a final year PhD student defending early October, supervised by Jan Olivier, who is a researcher at FAIR. I mainly worked in the domains of recurrent neural networks, generative models, and reinforcement learning. And at the moment, I'm mostly interested in reinforcement learning, probably with a focus on rewardless or sparse reward reinforcement learning, where basically you need to define a notion of what's interesting. Today, I'll be a bit more technical than that. I'm going to talk about invariance to time discretization as a general principle in machine learning. I'm going to try and show you how you can use this principle to design better algorithms. And I'll try to show that with the idea of invariance to time discretization, you can both derive empirical benefits and theoretical insights. So a bit of motivation to start with. The idea of invariance to time discretization, it comes from the fact that when you're faced with real-world data, most of the time, or at least sometimes, the data is inherently time continuous. For example, when you're looking at a visual stream, the visual stream is continuous. You only discretize it to make it processable by the computer. So discretization, it's only a trick. It's a trick that we have to use to make the data processable. And the intuition is that when you get to smaller time discretization, you only get more information about your data stream. So small time discretization should be associated with better performance. For example, in the case of video games, when a player has access to a better frame rate, basically is supposed to play better. Similarly, basically, when a player gets better APMs, better actions per minute, he typically plays better. So better discretization should be associated with better performance. But when you're using common machine learning or general algorithms, it may be the case that when you're discretizing at a finer grain, basically your performance are going to drop. And this is what we want to study, and we want to design algorithms that don't have this behavior. So now to define a precise framework about time discretization, the way I'm going to do this, I'm going to always assume that my data come from an inherently continuous data stream, which is simply going to be a sequence of data indexed by a time variable. And the time variable is going to be continuous. And now from this continuous stream of data, I can extract discretization. And to extract the discretization, I'm simply going to take a discretization time step that I'm usually going to denote delta t, and then extract the discretization. So the discretization of the initial data set is only going to be a discrete number of points, which are going to be x0, x delta t, x2 delta t, x3 delta t, etc. And the question we are going to ask is, when I'm processing the discretized data with my algorithm, how does the behavior of the algorithm changes when the time discretization changes? And typically, the big question is going to be what happens when the time discretization becomes small. Okay, as soon as we're talking about time discretization, there are two time notions that arise. There is the common notion of time in an algorithm, which is typically the number of steps, so simply the number of data points that the algorithm has treated. And then there's a second notion of time, which is the notion of time that is going to be of interest to us, which is the physical time, which is the amount of time that I've interacted with the data. And those two notions of times, they are related. Simply the physical time is the number of steps times the discretization time step. And so with the notion of physical time defined, I can define what I want for my algorithms. I can define the notion of invariance to time discretization. So what I'm going to say is that an algorithm is time discretization invariant if its behavior does not change when the time discretization change. And when I say the behavior does not change, I mean that when it's exposed to the same amount of data in terms of physical time, it learns the same thing. And it's only going to work when delta t is sufficiently small, that is when my discretization makes sense. Okay, so this is what we want to study in general for all algorithms, but in this talk we are going to focus on two sub-examples, which are an example in RL, namely I'm going to show you that Q-learning is not time discretization invariant, and I'm going to show you how to make it time discretization invariant. And secondly, I'm going to apply this to recurrent neural networks, and I'm going to show you that gated architectures in recurrent networks naturally arise when you're considering time discretization invariant networks. So first off, I'm going to talk about RL, and more precisely about frame rate robust Q-learning. So when I'm talking about frame rate, it's exactly the same as time discretization. The frame rate is typically only the inverse of the time discretization. So this is a work we presented at ICML 2019. A bit more on the motivation. So if you take any of your standard reinforcement learning algorithm, say you take DDPG or DQN or PPO, and instead of using the standard time discretization, you are going to use a much smaller time discretization. And now you can look at what's happening. So this is with low FPS or high time discretization. Standard case, you're training a DDPG algorithm and it works, kind of works, the robot is moving forward. Now, exactly the same, but this time I'm using high FPS or very small time discretization. So the agent can react much more quickly. You'd expect the agent to get better, but instead it gets completely worse, and even the agent does not learn anything. So I use the same algorithm, I tuned my hyperparameters, and yet the agent completely fails to learn. So if that's not enough to convince you that time discretization is important, because from this example, what you could tell me is simply that instead of considering my small time discretization, I could simply stack the frames and get my original time discretization back. Okay, but that's probably not the good approach, basically because it means that you're bottlenecking your algorithm instead of bottlenecking your hardware. Basically, when you get better hardware, most of the time you are going to get better sensors, better actuators, you are going to be able to react faster. And here what you're saying is, even if I'm able to react faster, I'm going to limit my hardware simply because my algorithms are not good enough. That's probably not the good approach. And the second reason, so we know that RL is typically not very robust. If you change a couple of hyperparameters, method that works on certain environments will completely fail. Here, this non-invariance to time discretization also contributes to the lack of robustness in deep RL. Namely, typically, as soon as you have a new environment, you typically have a new time discretization. So you are going to tune all of your hyperparameters without knowing how they interact with the time discretization. And so that means that you cannot provide sane defaults. Okay, so now that we know that this kind of problems seem to matter, how are we going to attack them? So to attack them, I need to define a notion of time discretization for reinforcement learning, and more precisely here for MDPs, so MDPs Markov decision processes, which are the usual framework of reinforcement learning. And the way I'm going to do this is first I'm going to define a notion of continuous Markov decision process, and then from this notion of continuous Markov decision process, I'm going to extract discretization, and I'm going to look at how the different quantities that I define on my discretization are going to evolve when I vary delta t. So let's do it. So to define a continuous MDP, basically a continuous MDP is quite close to a standard MDP. So it has a state space, which can be either discrete or continuous. Continuous, sorry, because we are in continuous time. An action space, which can be either discrete or continuous. Here I'm going to focus a bit more on discrete action spaces. And instead of having a transition kernel that tells you if I'm in state S and I'm doing action A, then where I'm going to be at the next time step, I have a state transition dynamic, which is the same thing but in continuous time. So it's basically a differential equation that links the temporal derivative of the states with the current state and the current action. And this continuous MDP is not properly speaking an MDP, because from this you cannot extract a proper transition kernel. But now from this continuous MDP you can extract discretization. And the way you're going to do it is simply by providing a Euler discretization of your differential equation. So you typically are going to keep your state space, keep your action space, and the only thing that differ is the transition dynamic, and your transition dynamic is simply the Euler discretization of your differential equation. And this time, discretized MDPs, they are actual MDPs. So they are proper environments that you can work with your RL algorithms. Basically because you can rephrase your second equation, the equation on the evolution of the state, as a transition kernel. So I mostly defined my MDP. There are still two components that are missing, namely the discount factor and the reward function. So when you're defining an RL environment, typically you also define a reward function, which tells you where you're good when you're not good. And you also define a discount factor. The discount factor is going to define the preference of the agent for the present. And another way to look at this discount factor is that it introduces a notion of temporal horizon, which is the number of steps on which you are going to optimize your return. If you're looking at rewards which are well above your temporal horizon, basically those rewards are going to amount for very little compared to current rewards. And so this temporal horizon most of the time is defined as 1 over 1 minus gamma, but this is in number of time steps. And as I've mentioned earlier, basically the number of time steps in a discretized MDP setup or in a continuous time MDP does not matter. What matters is the physical time. So I need to express this temporal horizon in terms of physical time, and to do this I simply have to multiply it by delta t. So I get a temporal horizon in physical time, which is delta t over 1 minus gamma. And now what I want to do is derive a scaling for gamma such that my temporal horizon converges to a proper limit when delta t goes to 0. Typically, if I take a gamma which is independent on delta t, what's going to happen is when delta t goes to 0, the numerator of my quantity is going to 0, the denominator is going to a constant, so this whole thing is going to 0. So I'm only considering instantaneous rewards. So that's not the proper scaling. What you can derive quite easily is that the proper scaling is to take gamma delta t to be gamma to the power delta t. And if you define your gamma in this way, you are going to obtain a limit for your temporal horizon in continuous time. And so that means that for sufficiently small delta t, you are always going to consider roughly the same temporal horizon in physical time. Everybody is following here? Okay, great. So this allows you to define the discount factor, and for a similar reason, you can see that the reward is going to scale linearly with the time discretization. So now that we've defined our continuous MDP and our discretized MDP, what we can start doing is looking at the different quantities which are useful in reinforcement learning and see how they behave when delta t goes to 0. So the first quantity we are going to look at is the v function, the value function. So the value function is the expectation of the return, knowing that I'm starting in a certain state. I can, of course, define it in all of my discretized MDPs because discretized MDPs are actual MDPs. And if I'm doing that, so I get a very nice expression. And this nice expression, I can see that it's a Riemann discretization of an integral. And so when delta t is going to 0, this sum is going to go to an integral, which I'm going to define as the v function of my continuous MDP. So this tells me that I have proper notion of continuous v function, which is the limit when delta t goes to 0 of the v function of my discrete MDPs. So the v function, everything is going well. I have a notion of v function, which is the limit of the v function in the discretized MDPs. So that's all great. So that's pretty much everything that is working in when you go from continuous time MDP to discrete time MDP. Now we are going to see things that are not working at all. So first thing that is not working, we have a problem with the Q function, namely that there is no continuous time Q function. I'm first going to give you a very rough intuition of why this is, and then a formal proof. So the idea of why there is no Q function is basically that the Q function, it gives you the dependency of the return on the first action you are taking. The problem is when your delta t is going to 0, the amount of time for which you are going to use the first action is becoming increasingly small. And basically when delta t goes completely to 0, this action is going to be used only instantaneously. And so it's only going to affect the whole trajectory a tiny bit. And that's pretty much what it says. The return is only going to be very slightly affected by a change of first action. And when delta t goes to 0, it's not going to be affected at all. So this tells you that the Q function is going to be independent on action when delta t goes to 0, which means that you won't be able to use it to select actions. So this is the intuition, and you can formalize it. So to do this, we're simply going to use the Bandman equation on the Q function in the discretized MDP. We are going to use a first-order Taylor expansion. And through this first-order Taylor expansion, we are going to show that Q pi is simply V pi plus a term of order O of delta t. And this term of order O of delta t, when delta t goes to 0, it's going to 0. So Q pi of SA converges to V pi of SA when delta t goes to 0. So this means there is no continuous time Q function. But more fundamentally, what this tells you is that there is no Q learning in continuous time. Because Q learning relies on the fact that when you have access to the Q function, you can use it to select better actions. But if your Q function is independent on actions, you cannot use it to select better actions. So this tells you that there is no continuous Q learning. Second thing, so I told you that there is no continuous Q learning, but you're not really interested in continuous time. You're actually interested in near continuous time. That is when delta t is small but non-zero. And here the problem basically remains. Why? Because your Q function is still equal to the V function plus a small term. And when you're going to try and learn the Q function, you're going to be able to learn pretty easily the V function, but learning the small O of delta t contribution, which is action dependent, this is going to be super hard. So you are going to learn the useless part of the Q function, but the action dependent part, you're not going to be able to learn it. And so Q learning is also expected to fail when you are in near continuous time. That is when delta t is close to 0. So that's the first problem. You have a second problem, which is a problem of exploration, and namely that when you're using epsilon greedy exploration, or more generally when you're using any exploration methods that sample independent noise at each time step, then basically your exploration method is not going to be to explore at all in continuous time. So epsilon greedy exploration, basically at each time step, either I'm using the argmax of the Q function with probability 1 minus epsilon, or I'm using a random action with probability epsilon. The problem is that the noise that you are injecting for exploration is independent at each time step. And without a notion of time correlation in your noise, you are not going to be exploring at all. So very quick example to exemplify that. So I'm a bit sorry, it's probably a bit technical here. But if you take a very simple environment where the derivative of your state is simply your action, and your action can be either -1 or 1, and you're using a fully exploratory behavior, typically you're only sampling with uniform probability -1 and 1, you can derive that the state that you are going to reach at time t plus 1, so t plus 1 is the physical time is t plus a physical time of 1. It's not t plus a single step. It's t plus a full physical time. So it means that to obtain st plus 1, I'm starting from st and I'm doing 1 over delta t steps. And during all those steps, I'm going to be sampling independent noise, which are all of variance delta t square and of mean 0. On this quantity, I can use the central limit theorem, and what I can show is that the overall noise contribution is going to be a normal distribution centered in 0 and with a variance of delta t. When delta t goes to 0, the variance goes to 0, so the noise goes to 0. So I'm not exploring at all. I'm using the most exploratory policy that I can find, and I'm not exploring at all. So this works in theory. Does this works in practice? So here I'm showing you an example on a pendulum. On the left you have a high time discretization. On the right, a small time discretization. So on the left you have something that is actually exploring with a pendulum that is actually circling around the origin. On the left, with a very small time discretization, you're not exploring at all. Okay, so now that I've explained what goes wrong, I'll now explain how to make this right. And the way we are going to do that is we are going to define continuous time quantities and then discretize them. And we are going to make sure that our continuous time quantities, they are well defined and they contain the information that we want. So first off, we said that the Q function was not the proper thing to learn. So what to learn instead? So what I told you is that the Q function and the V function, they only differed by a factor of order delta t. So what I can do is, instead of learning directly the Q function, I can try to learn instead the O of delta t term. And it turns out that this term is well defined, so I can define it simply as the difference between the Q function and the V function over delta t. It has a lot of good properties, so it admits a continuous time limit. To see that, you can simply use a Taylor expansion on the formula that you have here. Yeah?
Quick question here. Are you saying you're learning O as a function of t? Because otherwise it seems to collapse in exactly the same way as before.
So I'm not using the formula q pi minus v pi over delta t to learn A. Basically, A, it also verifies Bellman equations, which are a bit different than the equations on Q and V. And I'm using those equations to learn A. And using these equations, basically, I don't have the problem that Q minus V collapses, and thus I don't have any signal to learn. So A, it's going to admit a continuous time limit. This is pretty easy to show. Something which is less easy to show, but still true, is that A contains enough information to perform policy improvement. That is, if I'm taking an argmax on the action of A, I know that I'm using that the policy that I'm going to be deriving is better than my initial policy. So basically, A behaves the same in terms of information on action as Q. And finally, A is learnable. So that's exactly what I said. Basically, A, it verifies two Bellman equations, so a Bellman equation on V and a Bellman equation on A, which makes it learnable. And this was known before our work. That's basically advantage updating, which was introduced in the 90s. Now, so we know what quantity we want to learn. A small thing that remains is how to learn it, and notably how to select learning rates that are going to make my learning possible. Here, the problem is that when I'm learning in a deep learning setup, I'm typically not learning directly the function A, but parameters which are parameterizing the function A. And those parameters, they are going to be following parameter trajectories. And I need to verify that the behavior of my parameter trajectories when delta t goes to 0 remain well-defined. So what does it mean for the trajectories of the parameters to be well-defined when delta t goes to 0? It basically means that those parameter trajectories should verify a differential equation, either an ordinary differential equation or a stochastic one. And the fact that they are going to verify a differential equation or not is basically conditioned on the scalings of my learning rates. And what we showed is that if you don't use learning rate that scale linearly with delta t, then your learning is ill-behaved. If you're selecting the learning rates which are too big, basically you are going to diverge in a single step. And if you are using learning rates which are too small, you are not going to move at all. So this tells you that you have a very strict conditions on learning rates for it to work. Okay, so now we basically know how to learn, what to learn and how to learn it. The last thing that we want to take care of is exploration. Because as I said, if you have no temporal coherence in your exploration, in continuous time you're not exploring at all. So first off, what I mean by temporal coherence is that the noise that I'm using to explore at time t plus delta t should be quite close to the noise that I'm using at time t. And typically for discrete actions, that means that with high probability, the noise that I'm using at time t plus delta t should be the same as the noise that I'm using at time t. The way we are going to do that is we are going to define a temporally coherent noise, and then we are going to plug it into the Q-learning equations. And to define a temporally coherent noise, we're lucky we have access to such noise because statisticians always use them. So the first we could think of is probably the Brownian motion, which is temporally coherent. A problem with the Brownian motion is that it diverges as t goes to infinity. The Brownian motion also goes to infinity. So we are going to define a bounded, or at least a Brownian motion with a recall term, which is going to make it go back to the origin, which is the Ornstein-Uhlenbeck noise. And here, if you want an idea of the difference between an independent Gaussian noise and an Ornstein-Uhlenbeck noise, left is the independent Gaussian noise, no temporal coherency, while on the right you get an Ornstein-Uhlenbeck noise, where you can see a temporal coherence in what the noise is doing. Now that we've defined a temporally coherent noise, I still need to know how to use it to actually explore. So we want to perturb actions using this Ornstein-Uhlenbeck noise. We have two ways of doing that. So basically, when you have continuous actions, what you can do is simply add the Ornstein-Uhlenbeck noise directly into the action. That's what was done in dueling networks. Now, if you're in discrete time, it's not as simple, basically because you cannot add a continuous noise into discrete actions. So instead, what you are going to do is you are going to directly perturb the value of your Q function and then take the argmax on the perturbed value instead of directly taking it on the Q function. And this is going to give you an exploration method. And you can see that this actually explores both for tiny delta t's and for high delta t's. And if I remove the label on top of the two picture, I'm pretty sure that you couldn't recognize which is the small time discretization and which is the high time discretization. Okay, so we're all set. Now, if we plug all those tricks into, say, a DDPG algorithm or a DQN algorithm, is it working? So first we want a sanity check, a very simple example on which we can verify that we are actually time discretization invariant. Here we picked the pendulum environment because it gives you a nice representation of your policy in terms of your state, of your phase space. So here each little square represents the phase space of a pendulum. With on axis you have the angle, on ordinates you have the angular velocity, and when you have yellow means going right, black means going left, and the optimal policy for the pendulum is basically the policy that is learned everywhere on the right. And here I'm plotting the performance, or mostly the policy learned by the agent at different stages of learning in terms of physical time for different time discretization. And what you can see is that if you're taking the standard approach, so DDPG, what happens is that as soon as the discretization becomes a bit smaller, you are failing to learn, or at least learning takes much more time. While for our approach, so the approach where you plugged all the tricks into the method, you get a learning which is pretty much invariant. So you're learning the exact function in the same amount of time. Okay, so this gives you an idea of whether we are invariant or not. You can look at it in different environments. Here I picked the Mujoko Ant environment, and you have basically pretty similar results. So blue curves represent DDPG, red curves represent our method. When you get a curve which is lighter, this means that the discretization is smaller. What you can see is that for DDPG, as soon as you are getting smaller time discretization, your performance is worsening. For our algorithm, basically what happens is that the darker curves provides good performances, but as soon as you get a tiny bit smaller time discretization, you obtain better performances. When you reduce completely your time discretization, you still get a bit worse results. And this is related to the fact that our approach is not yet exactly time discretization invariant. There are still some slight limitations which make it so that when you're taking very small time discretization, you still get worse results. Okay, so that's pretty much it for a last result. So on the bipedal Walker environment, does this work? In low FPS, of course, it does. Now with high FPS, works too. So we've basically solved the problem we want to solve. Now we have a robot that is walking with a reaction time which is considerably reduced, relative to the first experiment. Now that I hope that I've convinced you that time discretization in reinforcement learning is important. I'm going to talk a bit, but in less details, about time discretization invariance in the context of RNNs, and this is part of the work that was presented at iClear 2018. So first off, I want to give a motivating example, which is very toy, but which gives you an intuition of what's happening. So consider you want to train a language model, and to train a language model, you are going to simply train a recurrent network to predict the next character in a sequence. You take an initial data set, which is your standard data set, and then you transform this data set by simply repeating each character. If you train a standard RNN on the first example, it's basically going to work. You are going to get a language model, not necessarily a good one, but at least with a given performance. And now you train the same standard RNN on the second task, and this time the performance as a language model that you are going to get is going to be much worse. So you have two ways of viewing this fact. The first standard way of viewing this is that standard recurrent networks, they are not able to handle long-term dependencies because there is a vanishing gradient problem. So basically, the gradient, when you backpropagate it for many steps, it tends to vanish. So that's a pretty good explanation, but it has some shortcomings. Namely, it does not give you much intuition on architecture. And secondly, there are some hypotheses when you're trying to demonstrate that vanishing gradient is existing that are not actually met in practice. The dual view of this problem is that you have a discretization problem, and namely a lack of invariance to time discretization. So here, what I've done, when I'm transforming the first sequence into the second sequence, I'm just changing my time discretization. I'm using a time discretization on the second sequence, which is 5 times less than the first time discretization. So here it's just a lack of invariance to time discretization that we're seeing. And the expectation that we can have from this example is that if we are able to design architecture which are actually time discretization invariant, we are going to be able to handle indefinitely long-term dependencies. Okay, so how are we going to design such architecture? The way we are going to do it is quite close to what we did with reinforcement learning. We are going to look at the initial RNN architecture, see it as a continuous time, look at its update equation, derive a continuous time equation which corresponds to my initial equation, and then change the discretization, see if the architecture that I'm using is changing or not. So first off, we are going to show that standard RNNs are not invariant to time discretization. So I'm giving you the standard RNN evolution equation, which is just an equation relating ht plus 1 to ht. This equation is simply the discretization with a time discretization of 1 of a continuous time equation. So here is the continuous time equation. And now what I'm going to do is I'm going to change the discretization. Instead of taking a time discretization of 1, I'm going to take an arbitrary time discretization of delta t. I'm plugging this discretization into my RNN equation, and what I end up with is a new equation. And what I want to know is whether this equation is the update equation of a standard RNN or not. And it's not, basically because I have terms that are appearing which are not present in my initial equation. I have the standard RNN part of the equation, which is the tan h term, but I have before it a scaling factor, which is not present in the initial equation, and I have a recall term. So these two parts were not present in my initial equation, so the update equation that I'm getting is not the update equation of a standard RNNs. Standard RNNs are not invariant to time discretization. So the question is, how do I make them invariant to time discretization? And that's pretty easy. Instead of using this architecture, I'm going to introduce new parameters to account for the recall term and the scaling factor. And this gives you this equation. So this is the equation of a leaky RNN, where I simply introduced a new parameter that corresponds to my time discretization. The alpha parameter is simply the delta t that you saw there. But now it's a learnable parameter. And now if I'm trying to change the time discretization in this new update with this new update equation, so I'm going from a time discretization of 1 to a time discretization of delta t, the new update equation that I'm getting still has the same form, so it comes from the same class of RNNs, but I simply changed the alpha parameter. The initial alpha parameter, I've transformed it to alpha times delta t. And this gives you a way to go from one time discretization to another time discretization. So leaky RNNs, they have a couple of nice properties. So just as I showed you, they are invariant to time discretization. And you have two interesting property, additional interesting property. Basically, as I told you, the alpha parameter, it can be interpreted as a time discretization. So the inverse of the alpha parameter, it gives you a notion of number of steps on which your dependencies are considered. So typically, if alpha is equal to, for example, 1/5, that means that you are considering dependencies which range roughly in 5 number of steps, in the number of steps of 5. And secondly, the alpha parameter, it kind of resembles the forget gate of an LSTM. The only difference is that for LSTM, the alpha parameter can vary with time. It can vary with the data that you are seeing, while here it is constant. And I'm going to come back to that a bit later. So if I come back to the motivating example with my two sequences, the first sequence where I had normal text, the second sequence normal text, but with each character replicated 5 times, and I train another leaky RNN on the first task. I obtain some parameters which are going to be good for my first task. What I can do is obtain good parameters for the second task, so the task where the time discretization was changed, simply by changing the value of alpha. If instead of taking alpha, I'm taking alpha over 5, I'm getting a new leaky RNN, which this time is good on the second task. And more importantly, if I have a good initialization for the first task, I can get a good initialization on the second task simply by taking my first initialization and dividing alpha 0 by 5. Because the architecture is not only time discretization invariant, but if I'm a bit cautious, the training process is also going to be time discretization invariant. So this is pretty much it for time discretization invariance. Now I'm going to give a couple of additional remarks before going into the results. So as I told you, the leaky RNN have an alpha parameter which kind of resembles the forget gates of LSTMs. But forget gates of LSTMs, they depend on data and they depend on time. So this gives you, in fact, a much stronger invariance property, which is an invariance to time discretization that can vary through time and that can vary depending on the data that you are receiving. So it's a much stronger time discretization invariance property. And most of the time, LSTMs, they also have multiple forget gates. So since forget gates, they are kind of equivalent to a notion of time discretization, that means that LSTMs are actually processing your data at multiple scales at once. And then your output layer is simply selecting which of those scales are relevant. And finally, so as we saw, forget gates, they are roughly equivalent to a notion of time discretization. So if I have a given data set where I know that I'm going to be considering time dependencies in a certain range, I can plug these prior on temporal ranges into the initialization of my LSTM so that I know that the LSTM is going to look precisely at those dependencies. So since each forget gate is going to act as a kind of chronometer for the given unit, this initialization dependent on the temporal ranges that you think you are going to receive, we call it chrono initialization. So now we want to test this out. So I'm going to show you two things. I'm going to show you that your training process is actually time discretization invariant when you're using leaky RNNs and gated RNNs. So I'm using a very simple task. The input sequence is a sequence of random characters, and I'm just trying to predict the previous character that I was given. If I'm changing the time discretization, the task becomes harder and harder because I have to remember characters for a longer period of time, but it's simply a change of time discretization. And what I'm going to be checking is that the performance of my network after a couple of epochs is the same or not. So you can achieve perfect training performance, and we are going to see whether the network is able to achieve perfect performance whatever the time discretization used. So here in blue you have the RNN curve. In red and violet you have the leaky RNN and the gated RNN curve. So on the left you have the dependency to time discretization when I'm considering uniform time discretization. So here I'm considering it in terms of maximum warping. The warping is the inverse of the discretization. And what you can see is that the performance of leaky RNNs and gated RNNs are invariant. They will always achieve optimal performance, while the performance of RNNs, it decreases when the discretization decreases or when the warping increases. And same thing for this time variable discretization. So I have a discretization that vary through time. As we saw, leaky RNNs are not perfectly invariant to variable discretization, but LSTMs or gated RNNs are. And so that's exactly what we see on the curve. RNNs are not time discretization invariant at all. Leaky RNN fail to be completely invariant when you consider very big warpings, and gated RNNs are perfectly invariant. Okay, and then is the initialization that we introduced useful? So here I'm considering two very standard tasks when you're trying to look at the long-term dependencies for recurrent networks. The first task is the adding task, where you're presented with two input sequences. The first input sequence is simply a sequence of random numbers. The second input sequence is a sequence of 0. You only have two elements in this second sequence that are non-zero. And the goal of the network is to output the sum of the two numbers which are non-zero in the second sequence. And the second task is the copy task. So you're inputting a number of bits to the network at time 0, and you're asking it to give it back to you after t time steps. So obviously considering long-term dependencies. And what you can show is that if you're initializing the biases of your LSTM properly on both tasks, you are learning much faster. So that's pretty much the takeaway here. If you know the temporal dependencies on your task, you can initialize the biases of your LSTM to handle them properly. Okay, so that's pretty much it. I want to wrap up very quickly and give you some quick takeaways. So here I've shown you that applying time discretization invariance principle to different domain of machine learning can get you theoretical benefits and practical benefits. I just want to give you a quick summary of the methodology. So what we've been doing, we're observing a discrete algorithm. We're looking at a continuous time counterpart of this algorithm, studying this counterpart, and seeing if it's stable by changes of time discretization. And you can apply it pretty much everywhere. So you can apply it to reinforcement learning, RNNs, model-based RL, exploration, etc. Now, there still are a couple of limitations to the approach. So first off, we are only approximately invariant. That means that our invariance property only holds as long as the discretization is a correct discretization, that is, that it's not too far from the continuous algorithm. If I'm taking a time discretization which is way too big, I'm too far from the continuous algorithm and I can't tell anything. Secondly, the algorithm that we define is often simplified compared to the actual algorithm, and typically the continuous time algorithm is often simplified, and typically there are some deep learning components that are hard to plug into continuous time algorithms, typically the optimizer, the replay buffers, things like that. So that's pretty much it. Thank you for listening, and if you have any question, I'd be glad to answer. Yep.
So sort of, you showed at the beginning the examples where if you go with delta t to almost 0,
yep,
right, then your environment or your task becomes yep, unsolvable unless you introduce your changes.
Yep.
Can you give an example of an environment or a task where you would need to go with delta t to almost 0 in order to solve it, right? So are there any tasks or environments that are unsolvable with big discretizations and become solvable with small discretizations and your changes?
So it pretty much depends on what you consider as small. Typically, the standard time discretization that you're using in reinforcement learning when you're considering video games is already quite small. It's 1/50, so it's small, and it's so video games in general. So when you're considering very easy video games, the time discretization that your algorithms are fit to actually handle the time discretization that you're looking at. But if you're looking at harder games, typically games where you need a long-range time dependencies, for example, I'm looking at StarCraft 2. Basically, for StarCraft 2, if you're using a very naive, for example, an exploration strategy which is not temporally coherent, you are going to fail, because basically when your units are going left and right in an incoherent manner, they are not going to move at all, or they are going to move only very slightly. So this pretty much depends on the difficulty of the task, and the more difficult your task, the more long-term the dependency that you are considering, the more you are going to need to consider time invariant algorithms. It's not only a question of time discretization, because the time discretization is basically arbitrary. It's a notion of relationship between your time discretization and your temporal horizon. So if the temporal horizon is long and the discretization is very long and the discretization is 1, your actual discretization and your actual need for temporal coherence is going to be, you are going to have a need for that.
So have you actually applied it to more complicated
No, because the paper is mostly theoretical at the moment. I know that some people which are working on things like, as I said, StarCraft, actually applied it and got slightly better results.
One could argue that, you don't need to go beyond the human frequency of actions, right? I mean, humans can act, 10 times a second or something like that, right? So there is no need to be more.
Once again, this time discretization is completely arbitrary. It depends on the horizon that you need to consider. If I'm looking at an environment where looking at the next second is sufficient, then I agree with you. But for example, if I need to consider time dependency which goes for years and years, even if I'm remaining at the same time discretization, I'm still going to have a problem with coherence, with time coherence. So the actual notion of time discretization, it actually depends on both the actual time discretization that you are considering, but also the temporal horizon. Basically, the two parameters, gamma and delta t, they are somewhat interchangeable. And what we've done is basically we've designed methods which are invariant to both changes of delta t or changes of gamma.
Thank you.
Yep.
Thanks for the fantastic talk, really enjoyed it. One question about kind of what's next. So you mentioned a few limitations here, but looking forward, what are the directions that you're really excited about?
So in the same kind of topics or on...
kind of personally, in the next 2 years, what would you work on?
Okay, so here what I've showed is probably very theoretical. I'm heading toward research direction which are maybe less theoretical and more into how to explore efficiently, how to design a notion of what's interesting in RL problems, notions of curiosity, things like that. On the same topic, I'd say that a natural extension to this kinds of methods would be looking at the problem with different delta t. So starting with a very coarse delta t, solving the problem with a very coarse delta t, and then use it as an initialization for a smaller delta t. That means that way you could have a full curriculum of task where you're considering a task with high delta t, you can solve it, but in a very rough manner. So basically you're going to have an agent which is very imprecise, and when you're lowering your delta t, you get better and better agents that are able to react much faster and much faster. That's the idea. Yep.
I have a question. Thanks for the great talk, by the way.
You're welcome.
So you had this update equation for the advantage function.
Yep.
Where in the denominator you had delta t.
Yep.
So you had a constant rescaling in the denominator.
Yep.
And now I'm wondering, if you were learning an advantage function using standard advantage, the advantage-Bellman equation, and an optimizer which is invariant to rescaling, something like Adam RMS prop or something like that, would you still need that division by delta t?
That's a good question. I'm pretty sure that you need it because basically when you're writing the equation on... So the idea here is just that we are going to be reparameterizing Q as V plus delta t A. And what you're suggesting is that we could simply reparameterize it as V plus A. And the fact is that you're not learning V and A independently. If you were, basically using Adam would indeed rescale the loss by the delta t factor which is present. But since you are updating V and A contiguously at the same time, you still have the dependency on delta t that is introduced. Basically, we tried learning Q as simply V plus A without the delta T factor, and it turns out that it does not work. It gives pretty much the same result as learning Q directly.
Mm-hmm.
So yeah, my guess would have to derive precisely the equations, but I think that Adam or RMS prop does not completely remove the problem.
Right. Thanks.
And even with Adam and RMS prop, you still have some slight problems when you're using a replay buffer, because when you're using a replay buffer with a different time discretization, you end up with a variance in your batch which is dependent on delta t, and since Adam or RMS prop is actually considering the variance, you end up with a variance that is with an update that is still depending on delta t. So the delta t factor does not completely cancels out. Yep.
So I was wondering, like, whether you have thought about like other discretization methods in your applications. Because, for example, if you think about, say, procedure sampling, people use HMC, and in HMC, people found that the simple Euler discretization is actually working very badly, and people instead using leapfrog, right? So I'm just wondering, in this context of, say, language modeling or like this RL context, whether any other, say, discretization methods can work.
I don't really know. I'm not very familiar with other discretization methods. Here we are mostly considering discretization as a given. So basically you have an environment with a given time discretization. You cannot necessarily play on it. If you can play on it, you can simply increase your time discretization, but not really decrease it. You can't always change your time discretization as you wish. So here it's more about given a time discretization that you have not necessarily the mean to change, can you produce an algorithm that will still work well? Am I clear?
Yes, sort of. But you know, the leapfrog method is kind of like you give it a time discretization, but you have, you know, say different update rates for different variables.
Okay. Same. I would need to look further into that, but that might be an interesting research direction. Yep.
I think we should wrap up. Sven Corentin again. If anybody that doesn't already have time with him today would like to, please reach out. We can set up time this afternoon to carry on.